Hello, everyone. Thank you so much for tuning in. This is the InnoQ Technology Lunch, and we've got an excellent talk for you today. My name is Jan Stumpian. I'm your host today. With me, there is Daniel Westheide. We're both based in Berlin, roughly 2 postcodes away from each other. But before we get to the talk, there's one more thing we would like to pitch, we'd like to announce. In 3 weeks' time, beginning of December, I believe that's December the 9th. We're organizing our conference where we're inviting everybody to join us. There are still free spots, and we will post a link in the chat in a second, and you're more than welcome to join us there. Excellent talks. It's a mix of content in German and English. I'm sure you will find something interesting for yourself there. Speaking about today, for a difference, we're streaming in English today. We've got an excellent talk from Daniel. Daniel is a Scala expert who wrote already 3 books about Scala, but we don't really mention the first one. Second, the following 2 books are really fantastic. I reviewed early copies of them and learned a ton about the language and idioms and patterns in the language. And today, Daniel is going to explore one of the topics he addressed in the second book, the topic of subtyping. And those of you who are connected to us live online right now, you're in luck because we are having a raffle. We have a physical copy of the newest book to share. We'll be following up in chat with a link to a forum where you can leave your email address, and we'll get in touch with one person who wins the physical copy of the book. With that behind us, I think we're ready to move on to the talk. Daniel, is there anything else I should add at the beginning? I think we're good to go.
I think we're good. Yeah.
Wonderful. Okay. Enjoy the show. And Daniel, the stream is yours. Take it away.
Yeah. Thanks, Jan, for introducing me. And hello, everyone. Thanks for being here. At this technology lunch, as Jan already said, I want to talk about subtyping and about the trouble with subtyping. And while I specifically want to talk about subtyping in Scala, I think you may also get something out of this talk if you work with other languages mostly. So let me quickly introduce myself. I'm Daniel. I work as a senior consultant in InnoQ. I'm also a co-organizer of Scala Bridge Berlin, which is currently in a hiatus due to the pandemic. And as Jan has said, I have written a few books about Scala. The first of this new series of books that I wrote is Scala from Scratch Exploration, and the second one, Scala from Scratch Understanding. You can get them as ebooks at Leanpub or as a hardcover at Blurb. And as Jan also said, today we're going to have a raffle. So there's one hardcover copy of the second book, which we want to give away to someone. And if you want to be that someone, you need to participate in this Google form. You have to be at least 18 years old, and you can't be a colleague of mine or a relative of a colleague of mine if you want to participate. And yeah, we will only use your data for drawing the prize, of course. All right, now that this is out of the way, let's finally get on topic. So I've been asking myself, what is it that draws people to Scala? And I think that most people who come to Scala do it because the language has a very strong functional foundation. But as we all probably know, however, Scala is a hybrid language, and apart from being functional, it's also object-oriented. Or more precise, it's class-oriented, and it supports subclassing. So by specifying that B is a subclass of A, 2 things are happening. First, there's code sharing. So B inherits the implementation of A, but there's also subtyping. So we can say B is an A. It has the same interface. Now, if we have subclassing, this actually makes the type system a lot more complex than if we don't have subtyping. So this is the troubles that I want to talk about. Before I started to work with Scala, I was mainly using Java for many, many years. And I've made an interesting observation there. So Scala's class-based inheritance is actually quite similar to what we have in Java. Nevertheless, many people who come to Scala from Java seem to have difficulties to understand concepts like variants, which exist to accommodate for subtyping. So me personally, for example, I have never heard about covariance or contravariance before I started to learn Scala. So today I want to explain type bounds and variants in Scala. And I want to demystify covariant and contravariant positions. And I also want to discuss some strategies that you can use to avoid some of the complexity of variants. And finally, there will be a very, very short outlook on a few changes in Scala 3 that have an effect on these strategies. So let's start with upper type bounds. Upper type bounds are something which you will probably come across quite often in a language like Java as well. And I think this is also why many people have a pretty good intuition for how upper type bounds work in Scala. I want to use an example of caffeinated beverages to explain this. So if you want to model them using subclassing, this is what it could look like. We could have an abstract base class caffeinated beverage, which says that there is a field caffeine content. And then we could define a bunch of subclasses, for example, filter coffee, black tea, or cute mate. Now we have a method that expects 2 drinks, and it is supposed to return the one with a higher caffeine content. The method is called choose. So this method works, but even if we pass in 2 values of the same subtype, then we lose the precision in the return type. For example, if we want to choose between 2 different filter coffees, the result is not known to be of type filter coffee anymore. It's a more general type. It's the type caffeinated beverage. Also, of course, we can choose between 2 values that are of different subtypes. For example, between a filter coffee and a black tea. Now, this may or may not be what you want. If we don't want to lose these precise types, maybe parametric polymorphism might be a solution. We need to abstract over the concrete type of beverage. So instead of having caffeinated beverage in our choose method, we use a type parameter A. Now, in this current version, you see here, this does not compile because the implementation of choose, it makes certain assumptions about A, right? Because it tries to access this caffeine content field. But we don't know anything about A right now. So we don't know that it has a caffeine content field. So what we need to do is add a constraint to our type parameter A. And in this example, the constraint is an upper type bound. So we say that A must be a subtype of caffeinated beverage. So now the compiler will only allow concrete types for A that are a subtype of caffeinated beverage. And this means that the implementation of choose now can really rely on the fact and access this caffeine content field of its arguments. So now, due to these upper type bounds, we can have more precise return types for our choose method. So if we pass in two values of type filter coffee, for example, to this choose method, the result will still be of type filter coffee. You can see that in these Scala REPL examples on the slide. And also, if we tie the type parameter of the choose method to be of type filter coffee, the compiler will now no longer allow us to pass in a value of some other subtype of caffeinated beverage. For example, we can't provide a cute mate as a second argument. Now, if we don't tie the type parameter A to a specific type, then we can still combine different subtypes of caffeinated beverage. For example, we can pass in a filter coffee and a cute mate, and then the Scala compiler will infer the return type, and it will be the most general and the most specific supertype. And that in this case is a product with caffeinated beverage with serializable. This is due to some quirks in the Scala type system. Okay, let's move on to variants. And again, we will continue with our example of caffeinated beverages. Maybe you've heard this joke that a programmer is just a machine that turns caffeine into code. Well, I don't really like the idea that we're machines, but the joke is still pretty nice for explaining covariance. So a programmer needs caffeine as input, and this caffeine must come from somewhere. So what we need is a caffeine source. But this caffeine source can be a source of different types based on the type of caffeinated beverage that they provide, right? So in this case, on this slide, we have a caffeine source of cute mate, and we also have a caffeine source of type filter coffee. And the caffeine source has a pull method, which you can call in order to get new beverages of the type of the caffeine source. And now let's have a look at how this caffeine source can be used. Agile Fragile is a consulting company, and this means that they are not very picky about the particular type of beverage that helps them stay caffeinated. So what they need is a caffeine source of type caffeinated beverage. So this is the most general type of caffeine source because caffeinated beverage is our abstract base class, right? Now, we know that filter coffee is a caffeinated beverage. So intuitively, a source that provides filter coffee should be a source of caffeinated beverage, right? However, the Scala compiler will not allow this. A filter coffee source is not actually a caffeine source of caffeinated beverage. And the reason is that caffeine source is invariant in its type parameter A. And what that means is that caffeine source of type filter coffee and caffeine source of type caffeinated beverage, they are completely different types. But the compiler gives us a hint how to solve this problem. It says that we may wish to define A as plus A instead. Or in other words, it says we should make caffeine source covariant in type A instead of invariant. But what does it mean that a type is covariant in type A? Well, let's have a look at this type crate, which is covariant in its type parameter A. Now, if an apple is a fruit, then a crate of apple is also a crate of fruits. So in other words, we can say if apple is a subtype of fruit, then crate of apple is also a subtype of crate of fruit. And we specify that a type is a covariant in a certain type parameter by using this plus symbol in front of the type parameter. So we can make caffeine source covariant in type A, and this allows us to assign an instance of filter coffee source to a value identifier with the type caffeine source of caffeinated beverage. The Scala collection library actually has quite a lot of collection types that are covariant in type A. And this is really in line with our intuition. So a filter coffee is a specific type of caffeinated beverage. So when we talk about multiple caffeinated beverages, then I guess most people would agree that a few filter coffees should be a valid example of that. Okay, so that was covariance. Let's continue with the opposite, which is contravariance, because this one is actually a bit less intuitive to many people. So we again continue with our example of caffeinated beverages. And maybe you have met these people who see programmers as resources that transform caffeine and a feature description into a deliverable. Now, the thing is that programmers can have peculiar tastes. Some programmers only consume filter coffee, and others only consume black tea. And maybe there are others who are less picky, who can consume any type of caffeinated beverage. So we have modeled this with a programmer class, which also has a type parameter A and an upper type bound for caffeinated beverage. And then it has this transform method where it expects caffeine and a feature and returns a deliverable. Okay, so let's move away from Agile Fragile to another company, which is called Startupper. So these people are poor, but they are also hip. So what they have is a caffeine source of Cute Mate, which means that they require a programmer who can consume Cute Mate. Someone who can transform Cute Mate lemonade into a deliverable. However, because they are Startupper, their only programmer is their CTO. And this CTO doesn't really care about the type of caffeinated beverage that they consume. As we can see on this slide, CTO is a programmer of type caffeinated beverage. So our intuition is probably that we can use a programmer who consumes any type of caffeinated beverage where we need a programmer who can consume Cute Mate lemonade. However, again, this does not compile because the Scala compiler expects a programmer of Cute Mate but found a programmer of caffeinated beverage. And again, the reason is that programmer is invariant in type A. And we get a suggestion to make programmer contravariant in type A instead. So what does it mean that a type is contravariant in type A? Well, first, again, the notation. This time we have to use the minus symbol in front of our type parameter to make our consumer contravariant in type A. So if an apple is a fruit, then a consumer of fruits is also a consumer of apples. In other words, if apple is a subtype of fruit, then consumer of fruit is a subtype of consumer of apple. So this is really the reverse situation to the covariant example. We can make our programmer class contravariant in type A by adding this minus symbol. And now it's possible for us to assign a value of type programmer of caffeinated beverage to a value identifier with the type programmer of QtMat. So this will now compile. But how do you actually know whether a class needs to be covariant, contravariant, or invariant in a specific type parameter? Well, for this, you will need to understand covariant and contravariant positions. We're going to start with covariant positions. So let's look at this function literal version of our pull method we defined earlier in caffeine source. So what we have here is a function with a return type filter coffee. And as you can see on the slide, we can assign this function to a value identifier whose type is unit to caffeinated beverage. So a function that returns something of type filter coffee is actually a subtype of a function that returns a caffeinated beverage. Now, why is that the case? The reason is that Scala has covariant return types. And by the way, if you're not actually working with Scala, but mostly with Java, in Java, this is exactly the same. So, for example, function 0 is covariant in its return type R, which you can see because of this plus symbol for the type parameter R. But the same principle also applies to methods. So Scala methods are also covariant in their return type. So if a class is covariant in a type A, it can only be used in covariant positions. And that means that it can be used either as a return type of a method, or as a type of an immutable field, or as a lower type bound for the type of a method parameter. Now, this third thing is something we will discuss a bit later when we talk about lower type bounds. However, let's first take a look at contravariant positions. We have a method that expects values of type caffeinated beverage. And it returns true if the first beverage it receives has more caffeine content than the second. So this is our method, has more caffeine content. We could also define it as a function literal instead. It doesn't really matter. And we also have a list of type filter coffee. And list has a method called sort with, which we want to use in order to sort this filter coffee. Now it's perfectly valid for us to pass in the method we defined above, which is of type caffeinated beverage, Boolean, even though the sort with method for a list of filter coffee, it expects a function whose input arguments are of type filter coffee. So because filter coffee is a caffeinated beverage, a function that expects caffeinated beverage is a function expecting filter coffee. It's just that such a function knows a bit less about the types of its input parameters. It's less specific. Now the reason is that Scala functions are contravariant in their input types. For example, function run is contravariant in its input type T1. On this slide, you see that T1 has a minus symbol in front of it in this signature. And again, not only Scala functions are contravariant in the input types, but also Scala methods. Okay. So if a class is contravariant in type A, it can only be used in contravariant position. And this means values of type A can only occur as a type of a method parameter. All right, So now we have covariance, we have contravariance. Let's move on to invariance, which we only very briefly touched when we saw that certain things were not possible because our classes were defined invariant within their type parameter. So in Scala, classes and traits are invariant in their type parameters by default. We saw that. And we also saw these problems it can cause. Now, let's try to see when invariance is actually necessary. So let's say that our caffeine source also needs a method called refill in addition to this pull method. And this refill method is supposed to be used, as the name says, to put in some new caffeinated beverage into our source. So it expects a value of type A. But we cannot simply add the method to a class the way it is now with A in being covariant. The compiler will now complain that the covariant type A occurs in contravariant position. And this happens because of our refill method, because it has an argument of type A, which is a contravariant position. So now we have values of type, where A actually occurs both in covariant and in contravariant position. So what can we do now? Well, now we need to make caffeine source invariant in type A. So basically this means all classes that are somehow mutable must be invariant in their type parameter. As a side note, it's probably a better idea to separate the refilling and the pulling into separate interfaces. So a programmer shouldn't really have to care about how this caffeine source is refilled, right? So having two separate interfaces for refilling and for pulling is likely a better choice. And it would also avoid that we have to introduce invariance here. Okay, if we have invariance like this, or if you have mutable classes, then we need to have invariance, as I said, and there's a good reason for that. In Java, arrays happen to be covariant in their type parameter. And this allows us to do a few dangerous things. For example, we can create an array of strings and assign it to an identifier with the type array of object. And once we have done that, we can actually put a number into this array of objects. However, this will also change the array of strings, right? Because this is actually still the same array, which will then lead to an exception at runtime. And here, Scala is playing it safe, and according to the rules of the Scala type system, array has to be invariant. So there's no way that you can create an array-like class that is covariant in its type parameter. Now, the final piece of the puzzle that you need to know about is lower type bounds. I've already mentioned them before, and it's actually quite difficult to see why you would need them. However, all of the things we have seen so far are somehow connected. And the reason why lower type bounds can be necessary is because of covariance. So I already mentioned that list, one of the Scala collection types, is covariant in type A. And this is because it's an immutable collection type. It has a method for prepending elements to the head of the list. That method is called : And you could think that this method might be defined as I've shown you on this slide. So it would receive an argument of type A and return a list of type A. It might surprise you that this doesn't actually compile. And the reason is that A occurs in contravariant position in this prepend method : However, we have defined lists to be covariant in type A, so this is not allowed. And this is where lower type bounds come to the rescue. So here's the actual definition of this prepend method called : in the Scala list type. So we add a type parameter b to the prepend method so that we can avoid using A in contravariant position. But we can't just accept any b, which we don't know anything about. We need a constraint. And because list is covariant in its type parameter A, this type B of the prepended element must be a supertype of A. And then we return a list of B. We declare a lower type bound by using this reverse symbol of an upper type bound. So it says B greater : A. Okay, so now you've also learned about lower type bounds. You have learned about invariance, contravariance, covariance. You've seen that things get quite complex due to subtyping and subclassing, more precisely. So maybe you think, why do we actually need to deal with this? And maybe there are some strategies for avoiding some of this complexity. Well, let's first have a look at common use cases for subclassing in Scala. Well, the first one would be modules, right? So we define an interface like user repository, and we have one or more classes implementing this interface or trait, implementing this contract, so to speak. So this is usually something that doesn't cause any problems because you rarely abstract over a module using a type parameter. Another use case is type class hierarchies. For example, we have a type class semigroup and a type class mono each, which extends semigroup. And also in this case, we really don't abstract over type classes using type parameters. So this shouldn't cause any problems. The main use case of subclassing in Scala, which is often problematic, is algebraic data types, which I will talk about now in a little bit more detail. And as for these classic object-oriented class hierarchies, as we had with caffeinated beverage, you should usually avoid them and instead model your domain with algebraic data types. Okay. As I already said, algebraic data types should be the default mechanism for modeling your application's domain. However, in Scala, the problem is that you need to implement them using subclassing. And we have an example of that on this slide. We have an abstract sealed class user, and we have two subclasses, authenticated and anonymous. Now, some other languages don't rely on subclassing for this. For example, Haskell uses data constructors and Rust uses something called variants. And in both cases, the only type that exists would be user in our example. There wouldn't be any subtypes, authenticated or anonymous. Actually, these languages, Haskell and Rust, don't have any notion of subtyping at all. The problem here is that subclassing is an implementation detail that actually leaks out into our API, right? which I've briefly defined on top of this slide. So this doesn't make use of lower type bounds. And the thing is now that we cannot create a list that contains both an anonymous user and an authenticated user. So first we create the empty list, then we prepend a list an item of type authenticated. So we would have a linked list of type authenticated, which means we can't prepend something of type anonymous now because our linked list is invariant. So there's one strategy which would make it easier to ignore the types of the subclasses that you need for algebraic data types. So what we can do is that we provide a factory method for each of our variants in our companion object of this abstract supertype. So in this case, in the user companion object. So we would have a method authenticated, which returns the authenticated variant, but using the return type user instead of authenticated. And we would do the same for anonymous. And now we can actually use these factory methods, and there's no problem with using an invariant linked list. We can create such a list consisting both anonymous users and authenticated users. However, this is not foolproof because it's still completely possible to use a regular apply factory methods of our case classes, which will then return the more specific type. Okay, as I promised, a very short outlook to what changes in this regard in Scala 3. Maybe you think that having to write all these factory methods for your algebraic data types is a bit tiresome. And also it leads to a lot of boilerplate code and noise, right? So let's see what changes in Scala 3 can help us there. So Scala 3 introduces this new enum syntax for algebraic data types, making them far less verbose than what you need to do in Scala 2. And under the hood, it would still generate case classes for you, which are subclasses of some sealed abstract class. However, the difference here is that the generated apply factory method on the companion objects, they don't expose the type of the subclass anymore. So in our example, the apply factory method for anonymous would return an anonymous user, but of type user, not of type anonymous. And the same for the authenticated variant, of course. So this makes Scala 3 enums easier to use with classes that are invariant in their type parameters. Nevertheless, of course, it remains important to understand subclassing, type bounds, and also variants. Because nothing has changed in Scala 3 about all the standard collection types and also the whole Scala ecosystem. You will see covariants and contravariants everywhere. So that's all I have for today. I hope I could help you gain a better understanding of subtyping in Scala and of the problems that arise out of it, and maybe also about how to cope with these problems. So the next time you see a compile error about variants or about type bounds, I hope you will have an easier time fixing those problems. I also want to use this opportunity to inform you again of the InnoQ Technology Day on the 9th of December. There will be some great talks there. Most of them are in German, but there are also plans for a few English talks in the evening. And as it happens, I will also have a talk at this technology day. And I think the schedule will shortly be announced. Okay. Thank you very much. And now I'm open for questions.
Wonderful.
And
thank you.
When it comes to the raffle, we are going to draw the prize or the winner directly after this talk.
Wonderful.
Actually, I have prepared some Scala code for that. So here I will pass in the participants and will randomly draw one of them. And I hope this implementation does the right thing. At least it's pure, as you
Perfect.
can see.
Oh, random is pure too.
Well, this nothing happens here, right? Because I'm using the state monad.
Fair enough.
Yeah, so this is why it's pure. It's just a dirty trick of functional programmers.
Wonderful. I love
Just
that trick. Fantastic.
delay the execution, right?
Thank you. Thank you very much for the informative talk. And yes, we are opening the floor to your questions. We already have the first one coming up. Daniel, you you enjoy to write books. You appear to be a serial offender at this point. When there will be another book about Scala 3? Any outlook?
Will there be, or what was it?
Will there be? But I'm asking, when will it be?
I'm not so sure, because I've just finished these two books, and it was a process taking several years, actually 3 or 4 years. So right now I'm in fact a bit tired of writing books, but so I can't promise anything right now. And I must say that there was a time when Scala 3 was approaching, and I had my doubts whether I shouldn't completely rewrite everything I already had and wait until Scala 3 is there.
Yeah.
But I decided obviously against that plan. Yeah. Maybe I will start with a few blog posts.
Excellent. Yeah. Get it going with some blog posts, and maybe this will combine to an interesting position on Scala 3. Fantastic. We don't have any immediate questions in the chat. Feel free to ask them if there's anything on your mind. Coffee is also an excellent topic to ask Daniel about. I can assure you of that. In the meantime, Daniel, you mentioned that Rust and Haskell don't have subtyping.
Yeah.
And is this the reason the problem of variance does not exist in those languages? Is this enough to like completely don't have this problem on your table?
Yeah, they don't have to deal with variance problems. So basically, any list, for example, would be invariant in these languages.
Gotcha.
Because subtyping simply doesn't exist. Yeah.
Gotcha.
It's a nice thing.
Yeah.
Scala, I guess, wanted to be a bit more compatible with Java in this regard. I guess that's probably the main reason why subtyping exists in Scala.
I see. So let me play it back for you to make sure that I understand. So that in order to have compatibility with Scala, with Java, with the base language, we need variance in order to still have this expressive Scala type system.
Yeah, if you want to interoperate with Java types, I think it's probably helpful if your own language also knows about subtypes. If some Java API uses subtyping and your own language doesn't have that concept, it might be difficult, right?
Interesting.
But
so
maybe
this must lead to interesting interoperability issues, right?
I mean, you are a Clojure person, Jan, so...
It happens to be true, yes.
With Clojure being dynamically typed, I guess you never have that problem.
Well, we have different problems, but yes, subtyping is not one of those problems. That's true.
Yeah, I actually recently read about
Clojure. I'm sorry?
Yeah, I recently read about this research language called Flix, which someone linked to in our Scala channel. Its syntax is heavily influenced by Scala, but it doesn't have any subtyping.
Oh, that's interesting.
And still it has Java interoperability. So it will be interesting to see what exactly they are doing there.
Okay, but you say it has Scala syntax, but I mean, Scala isn't about syntax, right? Scala is about the expressive type system to a large extent. And does it also have the same, well, not exactly the same, but similar expressiveness of the type system?
Yeah, I think so. I mean, I haven't looked at it in detail. There's not as much information about it, obviously, as about Scala, because it's still quite a young language.
For sure.
Yeah, but it looks quite similar.
Very interesting. Cool. I'll have to take a look at that. We have a question from the audience. Wouldn't the invariant linked list fail even earlier because it would expect type nothing because of nil?
Actually, that's an interesting question, but for some reason it does not fail, and I assume that it is type inference because the Scala compiler already sees the type of the first element, which is filter coffee. You also see that my nil there is actually not a case object as in the usual standard Scala list. In that Scala list, which is covariant, nil is a singleton object which extends list of nothing. This is not the case for the invariant list because it wouldn't actually work, because you need to have a type parameter if you have an invariant list. And that type parameter A seems to be inferred as filter coffee in our example. I hope that answered the question.
If it doesn't, let us know.
But it's
And
not a lot of code.
You can actually answering in the chat.
You can even try out this code yourself, define this invariant list. Yeah.
Very cool. Yeah, for those of you who haven't yet opened Daniel's book, his book is like full of code samples, examples. So it's not dry prose about type system. It's really one example after another, so that you can take every single page of the book, paste half of it in the repo, and it will compile. It's really cool that you can experiment with every single bit, which you can find there. Do we have any other questions? Because if we don't, then we will have to just go have a lunch.
Which was
There's nothing coming up.
Fine, of course.
Daniel, is there anything else you'd like to pitch, you'd like to mention? Where can people find you online? Oh, it's on the slide right now, isn't it?
Yeah, so I have a website, danielwestheide.com. I'm on Twitter as Kaffeecoder. My email address is also on this slide. If you want to approach me, daniel.westheide@inoq.com. Where else am I? I think that's the main sources where people can get in touch.
Fantastic. Cool. One last thing is an invitation again to our Technology Day happening on 9th of December. And on top of that, an invitation to the next technology lunch, which is happening as always in 1 week's time. We're going to have Sven Johan talking about, the title goes, Produktion, die vergessene Architektursicht. So we're going to finally discover what this production is all about and focus on it from the architectural perspective. We're switching back to German in that session. Please join us. I am certain it will be a whole lot of Spaß. And until then, I think we're good, right? We're wrapping it up and calling it a day. It's time for lunch for us.
Yeah, first we'll do the raffle, right?
The raffle, yes. We will do the raffle before the lunch. We can't do it during the stream because of privacy reasons, but that's you can guarantee that the code is type safe, so it's also safe for us to run it, and the raffle will be taken care of immediately, so that the person who wins the book gets the email shortly.
Yeah.
Perfect. Thank you all very much. Thank you for tuning in. See you next week.
Thank you.